All right, so we're continuing our talk on ideal gases. And so there's a lot of data you can look up on ideal gases, what's the density, that kind of stuff. And these are usually given at standard temperature and pressure. So that's abbreviated STP. STP stands for obviously what I just said, standard temperature and pressure. So standard temperature and pressure, standard temperature is defined as 0 degrees Celsius or 273.15 Kelvin, right? So it's actually quite cold. I don't know why they picked such a cold temperature for standard, but anyways. And then pressure is 1 atmosphere. So that one makes sense. Standard pressure is what the normal atmospheric pressure is. So if we think about ideal gases, they behave in the same fashion a lot of the times, right? Most gases are ideal gases, so they mostly behave the same. And so let's take a look at one of these properties, and that's called molar volume. And molar volume, as the name implies, is the volume of 1 mole of gas, right? So if we think about our PV equals nRT, we want to solve for V, right? So if we do that, divide both sides by P, so V equals nRT over P. And then let's think about what all these numerical values are. N here, we just said 1 mole, so that's fine. R is a constant, so that's fine. T is temperature, so we want to use the 273.15 Kelvin or 0 degrees Celsius, but you have to use the Kelvin. Actually, I guess you could change R if you really wanted to, but most of the time just use the Kelvin. Go with that. And then finally, pressure. Well, we got 1 atmosphere, so that's perfect right there. And remember, for R, the units are liters, atmospheres, moles, Kelvin. So all of these will cancel out from the other units except for liters. And if you go ahead, plug and chug those numbers, go ahead, take a minute and do that. Pause the video, do it. And then you get 22.4 liters, 22.4 liters. So almost, so we'll say like every gas at STP is approximately 22.4 liters. There are some deviations because no gas is 100% ideal, but they are very close. So no matter the gas, it's using up 22.4 liters if there's 1 mole of it. And so we think, oh, look, all the properties are the same, but they're not actually all the same. So let's take a look at these 3 balloons. They're all pictured here with 9 molecules. So I did actually count them. They all have 9 molecules each. So pretend those molecules are 1 mole, right? The volume of this balloon would be 22.4 liters, right? So they have the same number of moles and volume, but they're different gases. They're different. They have different identities, and so they have different molar masses. So if you put, 12 eggs in a balloon, that would weigh much less than 12 cars in a balloon. They would also want to take up the same volume, but you can, in this case, they will compare like, yeah, right? So they have different masses. Different masses. You can see these balloons weigh different amounts. The helium, much lighter atom, only weighs 4 grams. The ammonia, 17 grams, and then the O2, 32 grams. And so what we can say is that's different is the density, right? The mass is different, but the volume stays the same, so the density must be different. And they're all ideal gases, so we say PV equals nRT is true. And so then you can reorganize this equation, V equals nRT over P. And then you can take this value here, where V, and plug it into there, right? So you're going to take all of this and plug it into this place right here. And I'm going to draw in a bit of a weird way. You'll see why. This is a mass that stayed over there. Over N is equal to P over RT, right? So I just wrote it a little funky way, but if you do the algebra, this is what you'll get. And if we think about what's mass over moles, that's units of grams per mole, well, that's the molar mass. So I'm going to give the symbol mm. Double M will be our molar mass. So we can replace, let's see, go green, this double M for this mass over N. And so we'll get density is equal to molar mass times pressure over RT. And so basically what you can do here is you can find the molar mass of a gas and thus the identity of a gas by filling it up, say in a balloon and measuring the weight, right? Getting the density of it. So you'll see a cool example in lab. So you'll see EX in lab. And these are just basically plug and chug type of questions. So I won't go over one right now. We'll do one in the homework and whatnot. If you kind of want to be walked through it, check out exercise 19.12 and 19.13 in your book. So that's through OpenStax. Cool.